Quantum mechanics is the most successful theory in the history of science. It gave us lasers, transistors, MRI machines, and the entire digital age. But what does it actually tell us about reality? What is a quantum object when no one is looking? The first major attempt to answer this question emerged in the late 1920s from the collaboration between Niels Bohr and Werner Heisenberg in Copenhagen. It is now known as the Copenhagen interpretation, and it remains the most widely taught and referenced view of quantum mechanics. The Copenhagen interpretation is actually not a single unified doctrine. In fact, Bohr and Heisenberg never fully agreed on every detail, and neither used the term Copenhagen interpretation as a joint name for their ideas. The term was coined later by others, often by those who wanted to challenge what they saw as the dominant orthodoxy. Collecting observations with a mind cleansed of harmful preconceptions, it has been refined ever since. Welcome to Großdenken, everyone. Today, we are going to cut through the confusion and explain the core ideas that define the Copenhagen interpretation and why it remains so controversial. Please support this science channel grow by just subscribing. That would mean a great help. Despite internal disagreements, historians and philosophers have identified a set of principles that characterize the Copenhagen view. These include the emphasis on the role of the observer in quantum measurements, the indeterministic or probabilistic character of measurement outcomes, the principle of complementarity, which says that objects have mutually exclusive properties that cannot be observed simultaneously. The interpretation is built on Heisenberg's uncertainty principle, the idea that you cannot know both the position and momentum of a particle with unlimited precision. And it incorporates Max Born's statistical interpretation of the wavefunction, where the square of the wavefunction represents the probability of finding a particle in a particular state. Perhaps the most distinctive and controversial element of Bohr's view is his insistence that we must describe experiments using classical concepts, words like position, momentum, wave, and particle. Bohr famously argued that all experimental results must be expressed in ordinary language, the language of classical physics. Why? Because we need to communicate our findings to others unambiguously. But here is the twist. In quantum mechanics, the act of measurement inevitably disturbs the system being measured. You cannot simply observe a particle without affecting it. This is the quantum postulate that Bohr emphasized. Any observation of atomic phenomena involves an interaction with the measurement apparatus that cannot be neglected. This leads to the principle of complementarity, which is perhaps Bohr's most enduring contribution. Complementarity says that quantum objects can display wave-like or particle-like behavior, but never both at the same time. The two pictures are complementary but mutually exclusive. In the famous double-slit experiment, for example, if you set up the experiment to detect which slit a particle goes through, it behaves like a particle. If you remove the detector, it behaves like a wave. The behavior depends on the experimental context. Both descriptions are needed for a complete understanding, but they cannot be used simultaneously. Bohr took this even further. He argued that because the measurement apparatus and the object cannot be separated, we cannot speak of an independent reality in the classical sense. The properties we observe are not pre-existing in the object. They are brought into being by the measurement itself. The study was flawed. But here is the crucial point. The scientific process eventually corrected itself. This emphasis on the role of the observer has led to a major misconception. Many people believe the Copenhagen interpretation says that human consciousness causes the wave function to collapse. That is not what Bohr and Heisenberg argued. As Bohr himself said, "It is certainly not possible for the observer to influence the events which may appear under the conditions he has arranged." Bohr did not assign any special role to consciousness. The observer is simply the measuring apparatus or any physical system that interacts with the quantum object. The wave function collapses because of a physical interaction, not because a conscious mind looks at it. The subjectivist reading of the Copenhagen interpretation, which assigns a special role to human consciousness, actually arose later, partly due to the work of Eugene Wigner in the 1960s, and partly due to the construction of a unified orthodox narrative by Heisenberg in the 1950s. So what is the Copenhagen interpretation? It is the view that quantum mechanics is inherently probabilistic, that measurement inevitably disturbs the system, and that we must use classical language to describe experiments. It is the view that quantum objects have complementary properties that cannot be observed simultaneously. It is not a unified doctrine. Even its founders disagreed on key points. But despite its ambiguities and controversies, the Copenhagen interpretation has shaped how generations of physicists think about the quantum world. And it remains the starting point for any serious discussion of quantum foundations. Thanks for watching, and hit subscribe for more deep dives into the mysteries of science.